Now we move on to steps 3 and 4 of hypothesis testing. Step 3 is p-value. It is the conditional probability of getting a sample that produces a test statistic at least as extreme as the one calculated in step 2, assuming that the null hypothesis is true. If the p-value is small, then the null hypothesis is probably not true. Okay, so if we put what the p-value is in probability notation, it is equal to the probability of getting whatever test statistic we did in step 2, given that the null hypothesis is true. So whatever we have the parameter set to, assuming that that is true. Okay, so if it's a really high probability, okay, then it's likely that the assumption that we're making, that the null is true, is correct. But if it's a really low probability, then probably our assumption is incorrect. So this is how we calculate a p-value. It's actually really pretty straightforward. It's the area in the tail determined by the sign in the alternate hypothesis. So if we have a right-tailed test, which is one where in the alternate we've got a greater than, so right-tailed test, the p-value is the area to the right of the test statistic. Okay, so the p-value is that shaded area to the right. Okay, which we can find using our online probability calculator. Okay, left-tailed test, we've got a less than, and it is going to be the area. The p-value is the area to the left of the test statistic. Okay, so that's the p-value. And then if we've got a not equals in our alternate, then we get a two-tailed test. Okay, so we have our test statistic, a negative and a positive case. We can think of, well, the p-value is the area in those two tails combined. So in one tail, it's just half of the p-value. And then the other tail has the other half. So finding the p-value is just a matter of plugging in the test statistic into the online calculator. And let's do an example here. If we've got a test statistic of 1.34 and a right-tailed test, so we can mark our test statistic of 1.34 on our distribution, then the p-value is going to be this shaded area. That is the p-value. So if we plug that into our standard normal online calculator, right, we're going to plug in the 1.34, and if we want to make sure we select the option for the right tail, and that gives us a probability of 0.0901. Okay, 0.0901. And that's it. That's what we calculate for this third step, is that kind of value. All right, for a test statistic of plus or minus 1.34 in a two-tailed test, okay, so we've got two tails to the right of positive 1.34 and to the left of negative 1.34. So we are going to just plug in a 1.34 to the online calculator, and instead of choosing the right tail area, we want to choose the area in both tails. So if we plug that in, you get 0.1802, which you notice is also equal to 2 times what we got up above, 0.0901. All right, so because now it's just counting both tails. Okay, one more example. Let's say we have a test statistic of negative 2.94, and we've got a left-tailed test. Okay, so the p-value is that shaded area. plugging that into the online normal calculator. The p-value is 0.0016. Okay, so the probability that we get the test statistic of negative 2.94 given the null hypothesis is true is equal to 0.0016. Okay, if we want to put that in terms of the probability statement. Okay, let's look at another example. A normal distribution has standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. Our null is mu is less than or equal to 12, and our alternate is mu greater than 12. Find the test statistic and the p-value, and we'll draw the graph that shows the test statistic and the p-value. Okay, so we got to also determine what distribution we're going to use. It's about a mean, and so it's either going to be t or z, but we're given a population standard deviation. Okay, is 1, and we also have a sample size of greater than 30. So we'll assume we have normal and mean of 12 and standard deviation of 1 over square root 36. So the test statistic, z, is equal to that sample mean of 12.5 minus the value from the hypotheses, which is 12, and then we divide by 1 over square root 36. Well, that's going to give us a z value of 3. Okay, so that would have been step 2, finding the test statistic. Now we move on to step 3, finding the p-value. Okay, it's a right-tailed test. We go to the alternate, and it's a greater than. So the p-value is that shaded area. Plugging 3 into the online tool and selecting the right tail. Okay, we get a p-value of 0.0013. Okay, next example. U.S. Department of Energy reported that 51.7% of homes are heated by natural gas. A random sample of 221 homes in Newburgh found that 126 were heated by natural gas. Write the hypothesis to test if Newburgh has the same percentage as reported by the department. Find the test statistic and the p-value. So we'll start off with our hypotheses. So we got to figure out if which parameter, p or mu, and we got percentages going on, so it's going to be p. And what we're testing is to test if Newburgh has same percentage. The null will be p equal to 0.517, and the alternate will be p not equal to 0.517. So that's our hypotheses. Okay, this is about a proportion, so we know it's going to be normal. So we're going to have a z value that we're going to calculate, and we take p prime and minus the p-value from the hypotheses. All right, well, we're not really given p prime here. We have to calculate it. So let's start off with that. That's the sample proportion. We're just told that 126 out of the 221 homes that were sampled use natural gas, and that gives us a percentage or a sample proportion of 0.570. All right, we can use that to calculate the z value. So we take p prime, 0.57 minus p sub 0, 0.517, and then we divide by the standard deviation, which 0.517 times 1 minus that, which is 0.483. and then we divide by the sample size of 221. That gives us a test statistic of 1.58. Okay, so that's step 3. Now we move on. I'm sorry, that's step 2, the test statistic. Now we move on to step 3. Well, we've got a two-tailed test because we've got not equal in the alternate. Okay, so we have a 1.58 and a negative 1.58. And the p-value is the total shaded area to the right and to the left of those two values. Okay, so plugging those values into the online calculator, we get p-value equal to 0.1141. Okay, that takes us to step 4, where we come to the conclusion of the test, where we're going to reject the null hypothesis or not reject it. If we have a large p-value, okay, remember it's the probability of getting that test statistic under the assumption of the null hypothesis being true. If that is a large value, then there's a high probability that the sample occurring given the null hypothesis is true, and that's stronger evidence that the null hypothesis is true, and we should not reject it. And then on the other hand, a small p-value indicates low probability of that sample occurring given that the null hypothesis is true. And so it's stronger evidence that the null hypothesis is not true and we should reject it. So how do we decide whether the p-value is high or low? Well, we use a significance level, which we use alpha to stand for as what we compare. So just like with confidence intervals where we choose our level of confidence, in hypothesis testing we can choose our significance level alpha. And typically, most common is 0.05 and then 0.01 and 0.10 as well. Here's the rule to follow when making the conclusion. Reject the null hypothesis if the p-value is less than or equal to alpha, the chosen significance level, and do not reject the null if the p-value is greater than alpha, the significance level. So here are the p-values that we came up with for the practice problems for step 3. And so let's determine what we're going to do for the different significance levels. All right, so for number 1, 0.0901, okay, well, that is greater than 0.05 and 0.01. So we will, I'm going to abbreviate here, not reject or do not reject for alpha equal to 0.05 or 0.01. All right, but we will reject for alpha equal to 0.1 because it's less than 0.1. All right, it's greater than 0.05, 0.01, so we don't reject, but it's less than 0.1, so we do reject for that level of significance. Okay, 0.1802, well, that is greater than all 3 of the significance levels. Okay, so if it's greater than, we do not reject. So do not reject for alpha equal to 0.01, 0.05, or 0.10. All right, 0.0016. Okay, well, that is less than all 3, 0.01, 0.05, and 0.1, so we will reject the null hypothesis in that case for all 3 significance levels. Same exact thing for 0.0013. And then 0.1141, okay, well, that is greater than all 3 significance levels, so we do not reject. the null hypothesis. Okay, one more practice problem. A student academic group on campus decides that freshman students study at least 2.5 hours a day on average. One statistics class was skeptical, so the class took a random sample of 100 freshman students, found a mean study time of 140 minutes. The population standard deviation is 45 minutes. We're going to test using 3 significance levels. So we're starting from the first step here in our hypothesis testing. So we need our null and alternate hypotheses, and we have we're testing about a mean, so we got mu, and we are looking at this value of 2.5. So our null is equal to 2.5. Now let's figure out what symbol we put in the alternate. Okay, well, the first statement that's made is at least 2.5 hours a day. Okay, but the people that are testing it is the statistics class that are skeptical. So they're actually wanting to support the opposite claim, that it's less than 2.5. So that would be the null and alternate hypotheses. Okay, now for the test statistic, we can determine that the sample mean is going to be normal here because we have a known standard deviation from the population and sample of greater than 30. So the other thing we have to keep in mind here is we are given time in 2 units, hours, and also minutes. Well, we want to put that all in the same unit. So let's convert minutes to hours. Okay, so the standard deviation is given to us as 45 minutes, but in terms of hours, divide 45 by 60, we get 0.75. And we are given an X bar, a sample mean of 140 minutes. And if we convert that to, so this was hours, and if we convert that to hours, 140 over 60, we get 2.33 hours. So now let's calculate the test statistic. It's a z-value. Okay, we take X bar, 2.33 minus 2.5 over the population standard deviation of 0.75 divided by the square root of 100. And that gives us a test statistic, or a z-value of negative 2.27. Okay. Now the next step is to determine the p-value. All right, we've got a left-tailed test. There's our test statistic. Okay, we want this area is for the p-value. Okay, so looking that up, we get 0.0116 is the p-value. All right, now we're on to making the conclusion. Okay, so we're comparing this to all 3. So 0.0116 is greater than 0.01. So in that significance level, we are going to not reject. But 0.0116 is less than 0.05 and 0.1. So under those two, we would reject the null hypothesis. Okay, so different significance levels, we can have a different conclusion. Okay, this first part of hypothesis testing really is about the mechanics of doing the test. When we come back to part 2 later in the week, we're going to go through interpreting what these conclusions mean and kind of digging into it a little more deeper. So far, we're just focusing on just the mechanics, doing the calculation, kind of figuring out what that 4-step process is. All right, one more thing for you to do is the collaborative activity for this week. You want to conduct a hypothesis test for the claim that mean private university by state tuitions equals 200,000. For the sample that you had from last time for confidence intervals. Okay, so there's a new collaborate sheet posted. This time you'll want to just follow these steps. You're going to come up with the null and alternate hypotheses, and those really aren't, there isn't a place to put those necessarily on the collaborate sheet, but you can find the test statistic and enter that into the sheet, and then you can find the p-value and enter that into the sheet. I guess the other thing that you'll need to be able to do here is determine what distribution to use. So you can determine that. And then finally, conclusion, enter whether you are going to reject or not reject based on the given significance levels. My example is in there for you to follow. If you have any questions, let me know.